right, so I hope everyone is here today. Hi, my name is Jung Hwang, and today I will be leading this session. And the session is about hydrometeorological analysis techniques based on artificial intelligence and data. I would like to thank everyone here today for your time. We have 4 presenters here today, and each presenter will have 20 minutes to present their work. If you have any questions, I strongly recommend to ask questions after each presentations. So let us begin. So our first presenter, Jiang Wen Van from Kyungbuk University.
Hello everyone. Everyone hear me?
Yes.
Okay.
누구부터 시작하면 되나요?
Jiang Wen Van 경북대학교에서 오신 분부터 시작하면 될 것 같아요.
네.
Hello everyone, my name is Zhang. I come from the Kyungbuk Regional University. Now I'm a master student under supervisor Professor Gi Hali. So today I would like to share with you about our current research with title Machine Learning Algorithm for Mapping Multiple Satellite Precipitation Product over the South Koreans. My presentation includes 5 parts. The first one, introduction, and the second one is ensemble method. After that, I will move to precipitation data and then the result and ASNI conclusion. As you know, precipitation is one of the key components as well as the most challenging variable to estimate the hydrology cycle. It plays a crucial role in study of climate change, water resources management, and hydraulic forecasting. Rainfall is one of the main causes of natural disasters like flooding, landslide, drought, and soil erosion. And so that reason, accurate estimation of rainfall in different time scales are extremely important to quantity, not only for research, but also for practical applications, water resources management, as well as sporting decision maker. Nowadays, rainfall information were collected from the 3 main sources. The first one is Bay. It provides high accuracy at point scale and scarcely, but it still have several drawbacks like scarcely and uneven distributed in most regions of the world and costly to construction and maintain. So this use of only ground-based measurement to estimate spatial distribution of precipitation is subject to large uncertainty. The second one is radar-based. This radar precipitation provides highly resolution in both spatial and temporal scale. But the limited radar-based is only carries in some limited area and costly infrastructure construction and especially in the mountainous area and inaccuracy under complex atmosphere conditions. The third one is a satellite base. It provides rainfall estimated at global scale and it's available at no cost and near real times. And satellite-based information are highly valuable and have immense potential in water resources management, particularly for inaccessible, transparent, and poorly guided river basin. But the main drawback of satellite-based is that the multiple sources of error is still present, like failed detection, systematic and random errors, and the product tend to perform worse at shorter time scale like daily or sub-daily. So the main objective of our study is to, the first one, evaluate the accuracy of precipitation from various satellite sources at daily scale over the whole South Korea. The second one, mapping multiple sources of precipitation to obtain highly accurate rainfall data in the region of interest by using the random forest method. The last one, identify a suitable method that has high precision and easy to implement. single run depicts the overall process for merging multiple satellite data. Firstly, multiple data were downloaded from the internet. After that, it will be down scrolling by using nearest interpolation method in ArcGIS environment to 0.01. And then it will combine with the observation data were collected from the automatic weather station system through by several methods has named simple average, one outline remove average, inverse error, variance weighted, and random forest. And lastly, the merging precipitation product will be compared with the observation data from the automatic synoptic observation system ASOS. In our study, besides the random forest method, several statistical merging methods were also adopted. These include the simple average, one outline remove average, and inverse error variance weighting. As you know, nowadays, machine learning and deep learning receive a lot of attention from the scientists who are not working only not only working in data science field, but also in hydrological, because of it achieved a remarkable performance. Random forest is one of the most successful machine learning algorithms for practical applications. Because of it less prone to overfitting the decision tree and other algorithms. Random forest deal with complex or nonlinear relationship between inputs and outputs and no need rigid assumptions. It's easy to implement it, and random forests were successful applied to solve several problems like land shield, land cover, classification from the satellite images, or time series prediction. So that reason, random forests were chosen for merging multiple satellite precipitation in this study. In the random forest model is built on a lot of decision tree, and the input for each decision tree in the random forest model were to randomness by backing algorithm. And the final result when we working with the regression problems will be obtained by taking the average result from the R of the decision trees. Figure 2 describes the random forest was used in our study. Besides the multiple satellite product, we also use several auxiliary data like digital elevation or actually distance to account for the affected elevation on rainfall or geometric proximity. And South Korean were to as a case study in our research. The total of South Korean is approximately 100 kilometers square. The Asian moon sun is the main climate affected on the current, and the average annual precipitation is 1,270 millimeters per year. And data from the 384 stations of automatic weather station were used for training, whereas the data from the 64 stations of automated synoptic observation system were used for validation phase. Table 1 provides some primary information about the multiple satellite we use for merging processing. In our research, we use 4 satellite precipitation, namely chip, GS map, EMF, and TMM for the merging processing. Besides, we also use another product, namely multi-source weighted ensemble precipitation for comparison purpose. To evaluate the difference between the satellite precipitation product as well as the merging product with the observation data, in our research, we use several continuous index, namely clean soup time efficiency, root mean square errors, and mean absolute error to evaluate the accuracy and error of the satellite precipitation product. Besides, we also use some categorical metric, namely probability of detection, fail alarm ratio, and critical success index to access to the capability of the satellite precipitation product in the detection of rainfall event. So in the result, as you can see, the merging product often from the random forest has the highest accuracy, whereas it also has the lowest error when we use MAE or MSE. Is the capability of detection the rainfall event. The merging product often from the random forest method has the highest accuracy compared with another merging method with Fingerlam describes the correlation between the precipitation product and observation data for the whole period of time from the 2003-2007 at daily scale. As you can see, before we conduct the merging processing, almost the satellite precipitation product tend to overestimate or underestimate with the observation data. But the merging product often from the random forest has a relative good correlation with the observation data at the 64 station. A daily scale analysis table to provide comparison the accuracy of all precipitation product with the ground-based observation data from 2002-2007. As you can see, the merging product from the random forest has the highest correlation and KGE, while the lowest errors by when using the MAE or IMSE. In the capability of detection rainfall events, the low rain event were well captured by all products. The CSI presents the best performance for no rain events, followed by extreme events, and fail alarm rate value were consistently the worst for the light rain intensity. The POD and CSI of the merging product has highest value, while far is noticed when merged product were compared with other products. In conclusion, random forest were applied in order to obtain a suitable represent of precipitation patterns in the whole region of interest. Among different stacking methods, the merging method were carried out with multiple satellite products as a more suitable way than a single one. The performance of the merged product significantly increased when more rainfall stations were used to training model. And in the further investigation, lead more analysis about the satellite-based precipitation product at different spatial resolution and consider the influence of topographic factor. Thank you for your attention.
Thank you. So do we have any questions? Okay, then thank you very much. And we'll have our next presenter. So the next presenter will be myself. Yeah. Okay, so yeah, good morning. I am Jung-woo Hwang, currently working as a postdoc scientist at Columbia University. And today I am excited to have this opportunity to share my research of quantifying the spatial coherence of deficit and excess rainfall that happens across the continental United States. In general, when we encounter an extreme event, we often miss the news about other extreme events that happen at the same time in other areas. Interestingly, however, this kind of simultaneous extreme events have been happening consistently across the United States. Here, we define simultaneous events as events that occur within a same time frame, which in our case is annual, and we focus on rainfall events during this study. Across the continental United States, hydrometeorological extreme events have been occurring simultaneously every year. The figure shows an example of billion-dollar events that simultaneously occurred across the United States in 2019. Considering only such events that caused more than $1 billion in damages, the United States has experienced 9.8 events of severe storms or floods and 0.8 events of droughts from 2010 to the present on average each year, and multiple counties were affected by each of these events. The figure here illustrates examples of such simultaneous extreme wet and dry conditions for 4 different years. The red indicates dry precipitation anomalies, and blue indicates the wet precipitation anomalies. As shown in the figure, the contiguous United States has been under the influence of simultaneous wet and dry extremes every year, and the spatial distributions of those extremes varied over time. For example, a west, central, and southeast tripole-like pattern dominated 2007, while a northeast, and south dipole-like pattern dominated 2011. News reports of these simultaneous extremes also reflects the severeness of these events. So at a national scale, identifying such simultaneous extremes and modeling their manifestation as it relates to large-scale climate teleconnection drivers could be immensely beneficial for preparing for subsequent disasters and mitigating economic and societal damages. Therefore, this study focuses on developing a novel approach to systematically identify simultaneous extremes and testing if large-scale climate has any significant association with the manifestation of simultaneous extremes. The spatial temporal variability of extremes has been actively explored, mostly based on the classical return period thresholds. However, this classical approach fails to account for the spatial temporal dependence of hydrometeorological extremes. Spatial outliers or abnormal spatial patterns of simultaneous extremes could not be captured without considering their spatial temporal dependence. As hydrometeorological extreme events often affect large regions, their spatial outliers can have major impacts on mitigation plans and water resources management. A recent study shows there is a significant spatial dependence of hydrometeorological extremes across the contiguous United States, and thus it is critical to capture the spatial dependence of the simultaneous extremes that occur across the region, across the nation. To this end, this study introduces a novel approach to explore the simultaneous precipitation extremes across the contiguous United States on an annual basis, considering their spatial temporal dependence. And we also test the large-scale climate driver for their manifestation. With these purposes, we employed 114-year daily rainfall data from 1,244 GHCN stations distributed throughout the continental United States and tested ENSO to determine its control on the manifestation of simultaneous extremes. Considering the cumulative nature of hydrometeorological extremes and persistent effect of climate oscillations, we adopted and extended the concept of cumulative deficit index, which is called CDI. For this study, the CDI is modified to compute the annual maximum cumulative deficit between the long-term mean, the long-term mean daily rainfall and daily rainfall as a quantification measure for the annual maximum dryness of precipitation. Extending on this algorithm, we also developed another CDI-like index, which we refer to as the cumulative excess index, CEI, to represent the annual maximum witness of precipitation. The top figure on the left shows the rainfall events in blue bars and the long-term mean daily rainfall in red lines. Based on them, the cumulative deficits are calculated across the given year, and we choose the maximum value as the annual CDI for that station. And on the other hand, the cumulative excesses are calculated across the given year, and we choose the maximum cumulative excess as the annual CEI for that station. The approach of CDI is a nice way to capture the accumulation of precipitation extremes. For example, the largest precipitation happened around in day 140, but because of the accumulative deficits, it is not considered as an impactful event. There was a cumulative deficit in precipitation, and this precipitation event only offsetted the accumulative deficit. Meanwhile, a precipitation event that happened in near day 120 did not show a significant magnitude, but it recorded the highest CEI of that year. This is because of the antecedent precipitation events that accumulated the excess. To summarize, the CDI and CEI captures the antecedent conditions of the climate and is useful for capturing hydrometeorological extremes, which often occurs with duration. So based on this concept of CDI and CEI, the computing process is repeated for every station and year, and we eventually obtain a CDI matrix and a CEI matrix, which each dimension is 1244 by 114. To each CEI and CDI matrix, we apply the robust principal component analysis, the RPCA, to find the outliers of the matrix. The robust principal component analysis decomposes the given matrix into a low rank matrix and a sparse matrix by solving a convex program. The sparse matrix usually contains several non-value elements, which is expressed in 0 here. So in our case, for example, let's say we have a 10 by 5 CDI matrix. We take this matrix and decompose it into a low rank matrix and a sparse matrix using RPCA. The low rank matrix consists of CDI values with the spatial temporal outliers replaced with estimations from the RPCA. Here, the low rank matrix can be explained with its principal components. So we describe it as the spatial temporal variability of the expected CDI. Meanwhile, the sparse matrix, it contains the joint outliers of the original matrix. In our case, the sparse matrix is composed of outliers that are far off from the spatial temporal joint distribution of the CDI. The entries of the sparse matrix indicate the partial amount of CDI that couldn't be explained by the principal components. So we describe the sparse matrix as the spatial temporal variability of the unexpected amount of CDI. Since we are interested in these spatial temporal extremes, we focus on the events where the entry values of their sparse matrix is positive, which is colored in red here. And this selection allows us to focus on the spatial temporal extremes that have greater intensities. By repeating this process to the real CDI and CEI matrix, we can map the spatial distribution of the simultaneous dry and wet extremes across the United States for each year. So based on the RPCA of CDI and CEI matrices, we were also able to map the spatial variability of the extremes and the unexpected amount of the extremes across the United States. The first column of the figure shows the spatial variability of the dry extremes across the contiguous United States for 2 example years, 1991 and 2007. The second column of the figure displays the unexpected amount of dry extremes in a fractional form by computing the ratio of the sparse element to extreme CDI. By mapping the unexpected portion as percentage of the original extreme can provide invaluable information for risk management and water resources planning. The third and fourth column of the figure display the spatial variability of the wet extremes and the unexpected amount of those extremes in a fractional form, respectively. The spatial variability of the defined extremes mostly agrees to the annual precipitation anomalies for the sample years that we saw in the earlier slides. And as part of the study, we tested the large-scale climate impact on the simultaneous manifestation of spatial temporal extremes. Based on a binary matrix representing the manifestation of extremes, each CDI and CEI events were modeled based on a logistic regression on ENSO index. And the figures here show where the annual ENSO has a statistical significant association with the manifestation of spatial temporal extremes across the contiguous United States. In the figure, the contiguous United States is divided into 18 hydrological unit code basins to represent the hydrometeorological impact of the ENSO significant locations. As shown in the figure, the majority of the stations where the spatial temporal dry extremes show a negative association with ENSO are located vertically across the middle of the continental United States. And on the other hand, stations where the spatial temporal dry extremes show positive association with ENSO are in the northwest, Ohio Valley, southeast, and northeast regions. Shown in the right figure, the ENSO significant stations for spatial temporal wet extremes show a spatial distribution similar to that of dry extremes, but with directions reversed. So this study, the findings of this study are a novel approach for capturing the simultaneous spatial temporal precipitation extremes at the national scale was developed. And the manifestation of spatial temporal precipitation extremes have significant association with the ENSO in some areas in the United States. And this study showed significance in the approach that captures the spatial temporal joint of variability when identifying simultaneous hydrometeorological extremes. And the proposed approach does not rely on artificial threshold. And the proposed approach can be extended to other areas and for different types of events. Thank you. Do you have any questions? Okay. So shall we move on to our third presenter, Huang Wen Ti from Sejong University.
Yes, I'm here.
Yeah.
Can you listen? Can you hear me?
Yes.
잠시만요. Good morning, everyone. My name is Nguyen Thi Huong. I'm from Vietnam. I'm in master degree at Sejong University under Professor Hiên Han Quan supervisor. As you know, extreme drought and flood are among the most devastating natural hazards. So today we would like to present about assessing extreme flood and drought variability for the Korean Peninsula by using satellite data.
Excuse me, do you have a slide to present or just going to talk without it?
잠시만. Yeah, wait for me.
Okay.
Yes, it's here. And my presentation will be in 4 parts.
I cannot see your slides. Do you have any slides?
Slide, yeah. Oh, you can see. Wait for me.
Yes, now I can
Yeah,
see.
yes.
Yeah.
Sorry. And my presentation will be in 4 parts. Part one, background of the study, to meritor and material and methods, 3 results, and for conclusion and discussion. Background of the study, we will present the motivation and objectives. Flood causes damage to vegetation, agriculture, economy, causing food shortages, landslide, claiming more lives, human and wildlife. If flooding is often affects immediately, then drought is often referred to mystery slow motion. According to EPIC response report, over the last 2 decades, 1.65 billion people were adversely affected by flood and 1.43 billion people by droughts. 764 United States dollars billion in recorded damage. And the other motivation we would like to talk is the important role of measuring and monitoring extreme precipitation. Is it not possible to retrieve data from ground-based weather stations in North Korea? And extreme precipitation it depends on both of temporal and spatial dimension. Many studies indicated the GPM data have a good correlation with geyser observation on long-term scale, such as monthly, seasonally in hydrology and water resource management. Our study proposed of IMET data using IMET data over the last 20 years ago to comprehensive assessment of extreme events for the Korean Peninsula is what we aim to do. And next, we would like to discuss on material and methods. The input is the GPM IMET data launched in 2014 with monthly and 0.1 degree spatial temporal scale. IMET version 6 is a single interactive cost system for near real and post real time, include IMET early, IMET late, IMET final run. Time intervals are half-hourly and monthly. You see that only use IMET final run. IMET is used in many fields, and in hydrology, it is also very popular. And this is our study flowchart. After retrieving satellite data, we will determine the distribution of the data. Choose the model to analyze the trend and correlation between South Korea and North Korea, between South Korea and the Korean Peninsula, and between North Korea and the Korean Peninsula. Using next, we use SPI to identify precipitation abnormality and the transition period between extreme events. Next, compare satellite data with ground station data to determine correction factor. And finally, assess a variability between extreme drought and flood events for the Korean Peninsula. We use linear regression to consider the trend of monthly precipitation. SPI value is used to determine extreme events and validate satellite data with phase geyser data. Now we will discuss on the results. The result is with The first is IMS data. The second is the correlation of monthly precipitation between South Korea and the Korean Peninsula. And next, the trend of monthly precipitation and duration of transition of among extreme drought and flood events. And finally, a comprehensive assessment for the Korean Peninsula in the last 2 decades by using rigorous model and satellite data. Here you can see this map is the map show the monthly and seasonally precipitation in Korean Peninsula. In Korean summer is much wetter than the other season, and precipitation is mainly concentrated in July, the green and the yellow, and the lowest precipitation in December and January. This one. The results also show that precipitation is distributed in the South Korea, much than North Korea. Precipitation in South Korea tend to decrease significantly. Precipitation increased dramatically in 2020. So everywhere suffered to heavy damage to people and property. Taylor diagram are used to quantify the degree of corresponding between monthly precipitation of North Korea and the Korean Peninsula, between South Korea and North Korea, between South Korea and the Korean Peninsula. In terms of three statistics, Poisson correlation coefficient, the root mean square error, and the standard deviation. This one. Poisson correlation like this one. Poisson correlation, and this one is the root mean square error, and this one is the standard deviation. The trend in South Korea is similar to the Korean Peninsula more than the North Korea. The precipitation in South Korea and the Korean Peninsula decreased over 2 decades. Based on slope value, we can know the precipitation in North Korea increased by 13 millimeters. In South Korea, decreased by 16 millimeters, and the Korean Peninsula decreased by 3 millimeters. Results of in North Korea, duration of transition from extreme flood to extreme drought to 78 months, and should only 19 months to transition from extreme drought to extreme floods. In 2019, the country's leading newspaper Rodong Sinmun added that water is needed now more than ever, saying the country was in the fierce battle to prevent drought damage. In 2020, precipitation increased dramatically so the whole of Korea suffered heavy damage due to storm and flood. From 2013 to 2019, South Korea and the Korean Peninsula did not occur any extreme events but present decrease along with increased temperature 10 to 15 degrees. There is a high risk of drought in South Korea and the Korean Peninsula. In particular, in 2014, drought centered on the Han River area and according to Korea Climate Change Assessment Report 2020, and the Korea Peninsula faced severe drought for more than 3 years, 2013 to 2015, according to KWON 2016. Version 6 data depends on spatial temporal scale, so depend on the topography of the study area. Compares the satellite data with ground base station data is indispensable. At the current, we only validate for Seoul station, but in the future we will validate for whole South Korea. The results show that satellite data had high reliability, which can be effectively applied to the Korean Peninsula. Finally, we would like to summarize some of the obtained results and the expected result in the near future. Overall, the satellite data has shown quite accurately the period of extreme events over the last 2 decades. Our study provided assessment of extreme flood and drought variability for the Korean Peninsula. However, in the future, we need to continue to compare satellite data with data from other ground-based stations to retrieve the most reliable data. And that brings me to the end of my present. Thank you for your attention. I would be glad to answer any question you may have.
Do you have any questions? All right, so thank you very much.
Yeah.
And now we'll have Sumia Uranchimeg for Sejong University.
Yeah, I'm here. Good morning, everyone.
괜찮으신가요?
Good morning, everyone. Can you explain to can you disconnect your share?
Could you start sharing your screen?
Yeah, but the previous person's sharing speed.
Sumia, I can't not see your screen.
그 앞에 분이 화면 공유 꺼주셔야 되거든요.
Huang Wen-Ti, could you turn off your screen sharing? Huang Wen-Ti, could you turn off your screen sharing? Yes, thank you.
Let's see now. Can you see it now?
Yes.
Okay. Morning. My name is Sunya. I'm from Mongolia and working as a researcher with Honor Fund Professor at Sejong University. And today I'm talking about it's not the final results, it's kind of conceptual thing that we want to estimate hydrological state in engaged basins. So we are using one of the state variables, one of ancient runoff models, and its ability to represent hydrometeorological variables. Presentation will be in this. 첫 번째, hydrological growth refers to lack of water in hydrological system, such as low stream flow, low in lakes, reservoirs, and groundwaters. There's many hydrological growth indexes is available if you have observation data, but there's not many options for engaged basins. So the objective of the study is to generate information in engaged basins to use hydrological growth assessments. And the framework we are introducing also includes the optimization of rainfall runoff models and the visualization of the model parameters into the engaged basins. So the flow chart will be, we have meteorological data and hydrological data, which is used to model optimization of the model parameters, and after that we use watershed characteristics with popular function to generate parameters in the engaged basins, and after that we simulate the state variables in the engaged basins using the rainfall runoff model. So we will be doing analysis on correlation analysis on the state variables and hydrometeorological variables. This is method and data. We use GR4J model, which is daily number 4 parameter soil moisture accounting rainfall model, which is known to represent the observation rainfall very well, even though it has few parameters compared to the other hydrological models. The model has just only 4 parameters, and in the blue we have the 4 parameter explanation, and the X3, the third parameter, water bottom routing storage, is related to the area. So in this study, we are focusing on the standard basin areas, which is almost same in the area. So we will fix the third parameter into the optimization and visualization. And the state variables are extracted from the model and modify the codes to export these states with the runoff variable. We use the same multiple constraint areas and the upstream of the dam water level stays in the upstream of dam areas in order to generate natural outflow from and from basins. So we use data from 66 to 19 and all data is standard basin. Use the watershed characteristic data from WAMIS such as area, depth, and elevation of the basins. A total of 14 dams and 12 water level station data is used to optimization of the visualization of the model parameters. We use the SCMUA algorithm to optimize the model parameters, and for the optimization results show that after that 500 iteration, the almost in the versions form, so we use the SAS 1000 sample to generate the model parameter. This figure shows that we used optimized parameters to generate discharge in Chungju Dam and compare it with the tank model, which is used in the operational stage in Korea. So you can see that the GR4J model has only 4 parameters, which is considerably well presented the observation data. And the 14 dam inflow data also shown in these figures. You can see that it matches where produce the data. So the optimized parameters then take into the visualization. So we use some watershed characteristic to generate and make some find some relationship with the model parameters and make the visualization of the model parameters. So the function popular function is going to use the multivariate data analysis. It expresses relationship of the variables using the correlation. So each watershed pattern characteristic factors are the distribution and the function to generate the we do the cross validation for the 14 10 basins and 12 what the level stage data. Without the graph, we can see cross validation results blue line is result of the optimization, and red line is the result of the regeneration. There's some thing is not the magic part. The boundary, around boundaries. So we can use. And consider this is relatively way we visualize the parameter. It's the result of the cross-valence and cross-validation results. And the table shows that the optimized parameters and the visualization parameters and space. You can see that it is. You can see it is very short. Optimized parameters. Okay, what are the basis which is distributed more distributed where than the 10 on the side. So the generated parameters and the GR function model is to generate simple and state variables and cumulative testing. The state variables can compare with the ground of the field observation and real water observation. The temporal range of the solution data is 96 to 22. And groundwater field 6% groundwater pages and 10 real water field rates used to compare the state variables. And all you can see the groundwater field use groundwater field observation compared to the GR function state variable. And you can see the state variables. And in some stations, there is no correlation. But in general, you can see that there's more than 1.6. So the correlation of 27.6 or more, so which is considered very representative. And also the special comparison, special presentation of the contribution percent is shown in the figure on the maps, and you can see the some areas have and the green areas there's no ground of the page, so you can see the result of the special distribution of the sense. And this will be compared with the state variable, state variables with around the observation data, and you can see the trend is absolute value can be differs, but the trend is matches with each other. So from this, we can say the state variable can be used as alternative to groundwater value. As long as we are considering the growth index, which is the groundwater value data will be, even though groundwater data is changing with the index, so state variable is the groundwater value, which is the real water phase rate and same results. The correlation coefficient is the same, but some gauges shown this low correlation coefficient is only the conclusion data is not very pretty short. And also the more framework can be used assistant data the framework for the heteroscopy growth assistant in language spacing using speed variables of random and non-automatic exchange flow despite its it has few parameters compared to how function characteristic is used for the generalization of the method parameters. It's advantage of the four parameter of the method and the first education is that the generalization is not what this analysis returns in Hindu distinction on the possibility of speed variables as a joint evaluation of the ground of the field and field of the field. Framework can be used in the monitoring of the different hydrological study will be focused on the developing the growth using the speed variables instead of the ground of the field or what and would be very helpful for the engaged persons.
Recording in progress.
Okay, there were some technical issues, but yeah, thank you for your talk. Do you have any questions? All right, then I guess that's it for today. Thank you everyone for coming, and I hope see you again later by any chance. So thank you very much.
Thank you.
Thanks.